Right now, as you sit perfectly still reading these words, you are hurtling through space at 2 million kilometers per hour. Not because Earth is spinning, not because we orbit the Sun, not even because our solar system circles the Milky Way. No, something else is pulling us. Something massive. Something we cannot see. And it has been dragging our entire galaxy toward it for billions of years. In 1977, astronomers noticed something impossible. 7 independent teams, working at observatories across 3 continents, measured the motion of our galaxy through space. They expected to find us moving smoothly with the expansion of the universe, like a boat drifting on a calm cosmic ocean. Instead, they discovered we were racing toward a specific point in space at a speed that defied every prediction. The Milky Way, containing 400 billion stars, was being pulled like a leaf caught in an invisible current. When they calculated the force required to accelerate something as massive as our galaxy to such speeds, the numbers were staggering. Whatever was pulling us had to contain the mass of tens of thousands of galaxies. But when they pointed their telescopes toward that region of space, they saw nothing. The mystery deepened when astronomer Alan Dressler, working at the Carnegie Observatories in Pasadena, compiled data from over 400 galaxies in our cosmic neighborhood. Every single one was moving in the same direction. Andromeda, our nearest large galactic neighbor, 2.5 million light-years away. The Virgo cluster, containing over 2,000 galaxies. The Fornax cluster, the Eridanus supercluster. All of them, despite their enormous distances from each other, were falling toward the same invisible point. Dressler called it the Great Attractor. The name stuck, but it explained nothing. What could possibly be massive enough to pull thousands of galaxies across hundreds of millions of light-years of space? Here is what makes this truly unsettling. The Great Attractor lies in a direction we call the zone of avoidance. Imagine trying to see through a wall. That is what astronomers face when they look toward this region. The disk of our own Milky Way, thick with dust and stars and gas, blocks our view. We live inside the galaxy, embedded in its plane, and when we try to look through it toward the Great Attractor, it is like trying to see the horizon through a dense forest. Visible light cannot penetrate. For decades, we knew something enormous was pulling us, but we were cosmically blind to what it was. Think about that for a moment. We discovered an object so massive it dominates the motion of our entire region of the universe, and we cannot see it. Not because it is dark matter, not because it is a black hole, but because our own galaxy is in the way. It is as if you discovered that your house was sliding across the ground, pulled by some enormous force. But every time you tried to look out the window to see what was pulling you, the curtains were drawn. The breakthrough came in 1986, when astronomers began using infrared telescopes. Infrared light can penetrate dust that blocks visible light. The same way you can feel the heat of a fire through a closed door, even when you cannot see the flames. When they turned these instruments toward the zone of avoidance, they began to see through the cosmic fog. What they found was not a single object. It was a structure so vast it redefined our understanding of cosmic architecture. Behind the obscuring dust of the Milky Way lay the Norma cluster, a massive concentration of galaxies. Beyond that, the Centaurus supercluster. And beyond that, structures so large they had no names yet. But even these discoveries did not fully explain the Great Attractor. The mass they could see, even adding up all those clusters and superclusters, was not enough. The calculations still did not balance. Something was missing. Either there was even more mass hidden in the zone of avoidance that infrared could not reveal, or the Great Attractor itself was being pulled by something even larger. In 2005, astronomer R. Brent Tully at the University of Hawaii began mapping the three-dimensional structure of galaxies around us using a new technique. Instead of just measuring how fast galaxies were moving away from us due to cosmic expansion, he measured their peculiar velocities, the extra motion caused by gravitational attraction. It was like measuring not just how fast a river flows, but also the currents and eddies within it. He spent 9 years collecting data on 8,000 galaxies, measuring their distances and velocities with unprecedented precision. What emerged from this data was a revelation that changed everything. We do not live in a galaxy. We do not even live in a cluster of galaxies. We live in a supercluster so enormous that it contains 100,000 galaxies, stretches 520 million light-years across, and contains the mass of 100 quadrillion suns. Tully named it Laniakea, a Hawaiian word meaning immeasurable heaven. And the Great Attractor is not pulling us. It is simply the gravitational center of Laniakea, the basin toward which everything in our supercluster flows, like water spiraling toward a drain. Imagine you are standing in a vast valley. You cannot see the edges because fog obscures your vision in every direction. You notice that water is flowing past your feet, always in the same direction. You follow the flow and discover a stream. The stream joins other streams, forming a river. The river grows wider, joined by more tributaries, all flowing towards some distant point you cannot see. You are not being pulled by the destination. You are simply following the shape of the landscape, the natural topology carved by gravity over billions of years. That is Laniakea. That is where we live. But here is where the story takes another turn, one that reveals just how little we truly understand about the universe's structure. Laniakea itself is moving. The entire supercluster, with all its 100,000 galaxies, all its incomprehensible mass, is being pulled toward another structure. Astronomers call it the Shapley supercluster, located 650 million light-years away in the opposite direction from the Great Attractor. It contains the mass of tens of thousands of galaxies and appears to be pulling not just Laniakea, but multiple other superclusters toward it. We are falling toward the Great Attractor at 2 million kilometers per hour. The Great Attractor is falling toward the Shapley supercluster, and we do not yet know what, if anything, is pulling the Shapley supercluster. Let me give you a sense of the scales we are discussing. Light, the fastest thing in the universe, travels at 300,000 kilometers per second. At that speed, it takes light 8 minutes to reach Earth from the Sun. It takes 4 years to reach us from the nearest star. It takes 2.5 million years to reach us from Andromeda. The Great Attractor is 250 million light-years away. That means, when we observe it, we are seeing light that began its journey before the first dinosaurs walked on Earth. We are watching ancient history, cosmic archaeology written in the motion of galaxies. And yet, despite this enormous distance, despite the fact that we are separated from the Great Attractor by a gulf of space so vast that human minds cannot truly comprehend it, its gravity reaches across that void and pulls us. Every second of every day, for your entire life, for the entire history of human civilization, for the entire existence of Earth itself, we have been falling toward it. You have traveled billions of kilometers toward the Great Attractor, just in the time it took you to read these words. Now consider this. The universe is 13.8 billion years old. The Great Attractor has been pulling us for most of that time. At our current speed of 2 million kilometers per hour, we have already traveled an enormous distance toward it. And yet, we are still 250 million light-years away. We will never reach it. Not in your lifetime. Not in the lifetime of humanity. Not even in the lifetime of the Sun. Long before we could fall into the Great Attractor, the accelerating expansion of the universe will tear the cosmic web apart. The dark energy that drives this expansion is pushing space itself apart faster than gravity can pull it together. In the distant future, Laniakea will dissolve. The galaxies that now flow together toward a common center will be pushed apart, isolated, each one receding from the others, until they disappear beyond each other's cosmic horizons. But for now, in this brief cosmic moment, we are part of something larger. The discovery of Laniakea revealed that the universe is not a random scattering of galaxies. It has structure. It has architecture. Galaxies cluster into groups. Groups cluster into clusters. Clusters cluster into superclusters. And superclusters are connected by filaments of galaxies, vast cosmic highways of matter stretching across hundreds of millions of light-years, separated by enormous voids where almost nothing exists. If you could see the universe from outside, if you could zoom out far enough to see billions of light-years in a single view, it would look like a web, a foam, a sponge-like structure of matter and emptiness. Laniakea is one cell in that cosmic foam. The Great Attractor sits at the intersection of several of these filaments, a gravitational nexus where multiple streams of galaxies converge. It is not a single object. It is a region, a gravitational basin, the lowest point in the local cosmic landscape. Galaxies flow into it the way rivers flow into the sea, following the invisible contours of space-time carved by mass and energy over billions of years. And we are part of that flow, one galaxy among thousands, all following the same ancient paths. What does it mean to live in a universe like this? What does it mean to discover that your home, your planet, your star, your galaxy, your entire local group of galaxies is falling through space at speeds that dwarf anything in human experience, pulled by forces you cannot see toward destinations you will never reach? For most of human history, we believed Earth was the center of everything. The sun and stars revolved around us. Then we discovered Earth orbits the sun. Then we discovered the sun orbits the center of the Milky Way. Then we discovered the Milky Way is part of a local group of galaxies. Then we discovered the local group is part of the Virgo supercluster. And now we know the Virgo supercluster is just one lobe of Laniakea, and Laniakea itself is being pulled toward even larger structures. Each discovery has been a step away from centrality, a revelation that we are smaller and less significant than we thought. And yet, each discovery has also been a revelation of connection. We are not isolated. We are part of flows and structures that span the observable universe. The atoms in your body were forged in stars that lived and died billions of years ago. Those stars were part of galaxies that flowed through the cosmic web, pulled by the same forces that pull us now. You are made of matter that has been falling through the universe for longer than Earth has existed, following gravitational currents that were set in motion in the first moments after the Big Bang. The Great Attractor is not just a destination. It is a reminder that we are in motion, always in motion, even when we feel perfectly still. A reminder that the universe has structure and pattern and flow, even in the apparent chaos of billions of galaxies scattered across billions of light-years. A reminder that gravity, the weakest of the fundamental forces, the force you overcome every time you lift your hand, is also the force that shapes the largest structures in the universe, that pulls galaxies across cosmic voids, that determines the fate of superclusters. And here is perhaps the most profound realization. We discovered the Great Attractor not by seeing it, but by feeling its effects. We measured the motion of galaxies and worked backward to infer the presence of something massive. We used mathematics and physics to reveal what our eyes could not see. This is the power of science, the ability to extend our senses beyond their natural limits, to perceive the invisible, to measure the immeasurable, to comprehend the incomprehensible. We are blind creatures living inside a galaxy, obscured by dust and stars, and yet we have mapped the structure of the universe for hundreds of millions of light-years in every direction. We have traced the flows of matter across cosmic time. We have discovered that we live in Laniakea, in immeasurable heaven, falling forever toward a great attractor we will never reach. But the story does not end here, because every answer in cosmology raises new questions. If the Great Attractor is the center of Laniakea, and Laniakea is being pulled toward the Shapley supercluster, what is pulling the Shapley supercluster? Are there even larger structures, even greater attractors, beyond the limits of what we can currently observe? And what does this mean for our understanding of the universe's ultimate fate? To understand what we are falling toward, we must first understand what we are falling through. Space is not empty. This is perhaps the most important thing to grasp about the universe. When you look up at the night sky and see the darkness between stars, you are not seeing nothing. You are seeing something we cannot yet fully explain, something that makes up 68% of everything that exists. We call it dark energy. And it is tearing the universe apart even as gravity tries to hold it together. Here is the tension at the heart of cosmic structure. Gravity pulls. It attracts. It draws matter together into stars, galaxies, clusters, superclusters. It creates the flows we have been discussing, the currents that carry us toward the great attractor. But dark energy pushes. It does not push objects through space. It pushes space itself apart, stretching the fabric of the universe, accelerating its expansion. These two forces, gravity and dark energy, are locked in a cosmic struggle that determines the fate of everything. And right now, in our corner of the universe, in Laniakea, gravity is winning. But it will not win forever. Think of it this way. Imagine you are standing on a vast rubber sheet that is being stretched in all directions. Objects on the sheet, marbles representing galaxies, create dimples in the rubber. These dimples are gravity wells. Marbles near each other roll toward the deeper dimples, clustering together. But the sheet itself is expanding, pulling the marbles apart. If the expansion is slow enough, gravity can overcome it, and the marbles cluster. If the expansion is too fast, the marbles are pulled apart faster than they can roll together. The universe is that rubber sheet. Galaxies are the marbles, and the rate of expansion is accelerating. In 1998, two independent teams of astronomers studying distant supernovae made a discovery that shocked the scientific community. They were measuring how fast the universe was expanding at different points in cosmic history by observing exploding stars billions of light years away. They expected to find that the expansion was slowing down, decelerated by the gravitational pull of all the matter in the universe. Instead, they found the opposite. The expansion was speeding up. The universe was not just expanding, it was accelerating. Something was pushing space apart with increasing force. They called it dark energy. Not because they understood what it was, but because they had no idea what it was. It was dark in the sense of unknown, mysterious, invisible to all our instruments except through its gravitational effects. This discovery won the Nobel Prize in Physics in 2011. It also created a profound puzzle. If dark energy is pushing the universe apart, accelerating its expansion, how can structures like Laniakea exist? How can gravity pull galaxies together across hundreds of millions of light years when the space between them is expanding? The answer lies in the balance of forces and the history of the universe. In the early universe, matter was denser. Galaxies were closer together. The gravitational attraction between them was stronger. Dark energy existed even then, but its effect was weaker because it acts on space itself, and there was less space between objects. As the universe expanded, the density of matter decreased. Galaxies moved farther apart. But dark energy did not dilute. Its density remained constant, or possibly even increased. As space expanded, there was more space, and therefore more dark energy. Eventually, around 4 billion years ago, dark energy became the dominant force in the universe. The expansion began to accelerate. But by that time, structures like Laniakea had already formed. Gravity had already pulled galaxies into clusters and superclusters. These structures were gravitationally bound, meaning the mutual gravitational attraction of their components was strong enough to overcome the expansion of space. Think of it like a rope tied between two boats on an expanding ocean. If the rope is strong enough, the boats stay together even as the ocean grows larger around them. Laniakea is that rope. The great attractor is the knot at its center. However, this gravitational binding has limits. Laniakea is held together. The local group, containing the Milky Way and Andromeda and about 50 smaller galaxies, is held together. But the space between Laniakea and other superclusters is expanding faster than gravity can pull them together. In the future, as dark energy continues to accelerate the expansion, even structures like Laniakea will begin to dissolve. The galaxies at the edges will be pushed away. The supercluster will shrink. Eventually, billions of years from now, only gravitationally bound groups like our local group will remain. Isolated islands in an expanding cosmic ocean, unable to see or reach any other islands. But we are not there yet. Right now, we live in what cosmologists call the age of structure. Galaxies cluster, superclusters flow, the cosmic web is visible, and the Great Attractor is the center of our local flow. To understand it better, we need to understand what it is made of. And that brings us to another invisible component of the universe, one that is even more mysterious than dark energy: dark matter. When astronomers add up all the visible matter in the universe, all the stars and gas and dust they can see with telescopes, they find it accounts for only about 5% of the total mass and energy. Dark energy accounts for 68%. That leaves 27% unaccounted for. This missing mass reveals itself through gravity. Galaxies rotate too fast. The stars at their edges should fly off into space, but they do not. Something invisible is holding them together. Galaxy clusters contain more gravitational mass than we can see. The light from distant galaxies is bent by gravitational lensing as it passes through clusters, and the amount of bending indicates far more mass than the visible matter can explain. This invisible mass is dark matter. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation at all. We know it exists only because we can see its gravitational effects. The Great Attractor is not just a concentration of galaxies. It is a concentration of dark matter. In fact, most of its mass is dark matter. The galaxies we can see, even with infrared telescopes piercing the zone of avoidance, are just tracers, visible markers of a much larger, invisible structure. Imagine an iceberg. The part above water is the visible matter, the galaxies and stars. The part below water, far more massive, is the dark matter. The Great Attractor is an iceberg of cosmic proportions. Scientists have created simulations of cosmic structure formation, running supercomputers for months to model how matter clumps together under gravity over billions of years. They start with the conditions of the early universe, tiny fluctuations in density left over from the Big Bang. Then, they let gravity do its work, pulling matter together, forming the first stars, the first galaxies, the first clusters. These simulations include dark matter, because without it, the structures do not form correctly. Visible matter alone cannot create the universe we observe. But when they include dark matter, the simulations produce a cosmic web that looks remarkably like what we see through our telescopes. Filaments of galaxies, vast voids, clusters at the intersections of filaments, and superclusters like Laniakea. In these simulations, dark matter forms the scaffolding. It clumps first, creating gravitational wells. Then, visible matter, gas and dust, falls into those wells, forming stars and galaxies. The galaxies we see are like lights on a Christmas tree. The tree itself, the structure that holds the lights, is dark matter. The Great Attractor is a particularly dense knot in that tree, a place where multiple filaments of dark matter intersect, creating a deep gravitational well that pulls everything nearby toward it. But here is what makes this truly fascinating. We do not know what dark matter is. We know it has mass. We know it interacts through gravity. But we do not know what particles it is made of. It is not atoms. It is not protons or neutrons or electrons. It is something else, something that does not interact with light or electromagnetic fields. Scientists have built detectors deep underground, shielded from cosmic rays, trying to catch dark matter particles as they pass through Earth. So far, they have found nothing conclusive. Dark matter remains one of the greatest unsolved mysteries in physics, and yet it shapes the largest structures in the universe. It determines where galaxies form. It creates the flows that carry us toward the great attractor. We are being pulled by something we cannot see, made of something we do not understand, toward a destination we will never reach. Let me give you another way to think about this. Imagine you are a fish living in the ocean. You can see other fish. You can see coral and rocks and seaweed. But you cannot see the water itself. It is invisible to you. Yet the water determines everything about your life. It carries you in currents. It transmits pressure waves you sense as sound. It shapes the environment you live in. Dark matter is like that water. It is the medium in which galaxies swim, invisible but essential, shaping everything without being seen. Now, let us return to the question of measurement. How do we know any of this? How do we measure the invisible? How do we map structures hundreds of millions of light-years away when we cannot even see through our own galaxy? The answer lies in a technique called redshift mapping, and it is one of the most elegant methods in all of astronomy. When an object moves away from you, the light it emits is stretched. The wavelengths become longer. For visible light, this means the light shifts toward the red end of the spectrum. This is called redshift, and it is the same phenomenon as the Doppler effect you hear when an ambulance passes you, its siren dropping in pitch as it moves away. In the universe, galaxies are moving away from us because space itself is expanding. The farther away a galaxy is, the faster it is receding, and the more its light is redshifted. By measuring the redshift of a galaxy, astronomers can determine its distance. But galaxies are not just moving with the expansion of the universe. They also have peculiar velocities, extra motion caused by gravitational attraction. If a galaxy is being pulled toward the great attractor, it has a component of motion toward us, or away from us, that is separate from the expansion. By carefully measuring the redshift and comparing it to the expected redshift based on distance, astronomers can calculate this peculiar velocity. And by mapping the peculiar velocities of thousands of galaxies, they can trace the flows of matter through space. This is what Brent Tully did when he discovered Laniakea. He measured the peculiar velocities of 8,000 galaxies. He created a three-dimensional map showing not just where galaxies are, but how they are moving. And when he analyzed that map, he saw the flows. He saw streams of galaxies converging toward the great attractor. He saw the boundaries where flows from different superclusters met. He saw the shape of Laniakea emerge from the data like a coastline appearing through fog. Imagine you are trying to map an invisible landscape using only the motion of leaves floating on water. You cannot see the hills and valleys beneath the surface, but you can see which way the water flows. By tracking thousands of leaves, you can infer the shape of the land. That is what Tully did with galaxies. He used their motion to reveal the invisible structure of dark matter, the gravitational landscape that shapes the universe. But this technique has limits. We can only measure peculiar velocities for galaxies that are relatively nearby, within a few hundred million light-years. Beyond that, the expansion of the universe dominates, and the peculiar velocities become too small to measure accurately. This means our map of cosmic flows is limited to our local region of the universe. We can see Laniakea. We can see that Laniakea is being pulled toward the Shapley supercluster, but we cannot map the flows beyond that. We do not know if there are even larger structures, even greater attractors, pulling the Shapley supercluster. We are like cartographers in the age of exploration, mapping the coastlines we can reach, knowing that vast continents lie beyond our current range. There is another technique astronomers use to study large-scale structure, one that does not rely on measuring individual galaxy velocities. It is called gravitational lensing, and it allows us to map dark matter directly. When light from a distant galaxy passes near a massive object, the gravity of that object bends the light, acting like a lens. If the lensing object is very massive, like a galaxy cluster, It can create multiple images of the background galaxy, or stretch it into arcs and rings. By studying these distortions, astronomers can map the distribution of mass in the lensing object, including the dark matter. This technique has been used to create maps of dark matter in galaxy clusters, revealing the invisible scaffolding that holds them together. It has shown that dark matter is not evenly distributed. It clumps and filaments, just like visible matter, but on even larger scales. And it has confirmed what the simulations predicted. The universe is a web of dark matter filaments, with galaxy clusters at the intersections and vast voids in between. The Great Attractor lies at one of these intersections. It is a node in the cosmic web, a place where multiple filaments converge. The galaxies we see falling toward it are following the filaments, like ants following pheromone trails. And we are one of those ants, crawling along a filament of dark matter that stretches across Laniakea, pulled by gravity toward a destination we cannot see. Now, consider the timescales involved. The universe is 13.8 billion years old. The first galaxies formed a few hundred million years after the Big Bang. The cosmic web began to take shape as gravity pulled matter together along the densest filaments. Laniakea formed over billions of years as galaxies flowed together, as clusters merged, as the structure we see today gradually emerged from the primordial chaos. The Great Attractor has been pulling us for most of the age of the universe. We have been falling toward it since before the Sun existed, since before Earth formed, since before life began. And yet, we only discovered it 49 years ago. For all of human history, for all the millennia that humans have looked up at the stars and wondered about their place in the cosmos, we did not know we were falling. We did not know about the Great Attractor. We did not know about Laniakea. We did not know about the cosmic web. We thought the universe was static, or expanding uniformly, or collapsing. We did not know about dark matter or dark energy. We did not know that 95% of the universe is invisible to us. This is the power and the humility of science. The power to discover what was always there but never seen. The humility to accept how much we do not know. Every answer raises new questions. Every discovery reveals new mysteries. We have mapped Laniakea, but we do not know what dark matter is. We have measured the acceleration of the universe, but we do not know what dark energy is. We have traced the flows of galaxies, but we do not know what lies beyond the limits of our observations. And there is something profound in that. We are creatures who evolved on a small planet, orbiting an ordinary star in an unremarkable galaxy, and yet we have reached out with our minds and our instruments and touched the largest structures in the universe. We have measured the invisible. We have mapped the immeasurable. We have discovered that we live in a supercluster called Laniakea, that we are falling toward the Great Attractor at 2 million kilometers per hour, that we are part of flows and structures that span hundreds of millions of light years. But the story is not complete, because there is another layer to this, another way in which the Great Attractor challenges our understanding. It is not just about where we are going, it is about where we came from. The flows we see today, the motion toward the Great Attractor, are the result of initial conditions set in the first moments after the Big Bang. Tiny quantum fluctuations in the density of matter, inflated to cosmic scales by a period of exponential expansion called inflation, became the seeds of all structure. The densest regions attracted more matter. The voids became emptier. Over billions of years, gravity amplified these tiny differences into the cosmic web we see today. This means the Great Attractor is not just pulling us. It is the result of a process that began 13.8 billion years ago, a process that connects the smallest scales of quantum mechanics to the largest scales of cosmology. The fact that we are falling toward it is a consequence of the initial conditions of the universe, written into the fabric of space-time in the first fraction of a second after the Big Bang. We are following a path that was set before the first stars ignited, before the first galaxies formed, before anything we would recognize as structure existed. And here is where the philosophical weight of this discovery becomes almost unbearable. We are not just moving through space, we are moving through time. The light we see from distant galaxies left them millions or billions of years ago. When we look at the Great Attractor, we are seeing it as it was 250 million years ago. We are seeing the past. And the galaxies near the Great Attractor, if they have astronomers looking back at us, are seeing the Milky Way as it was 250 million years ago, long before humans existed, before mammals dominated the Earth, when dinosaurs were just beginning to evolve. We are all moving through space-time, following paths carved by gravity, paths that connect us across vast distances and vast times. The Great Attractor is not just a place, it is a moment in cosmic history, a configuration of matter and energy that existed in the deep past and will exist in the far future, but which we can only observe as it was, not as it is. We are falling toward a destination that has already changed, that is already different from what we see, that we will never reach because the universe is expanding too fast. This is the nature of cosmic observation. We are always looking at the past. The farther we look, the deeper into history we see. The most distant galaxies we can observe are so far away that their light has been traveling toward us for over 13 billion years. We are seeing them as they were when the universe was young, when the first stars were forming, when the cosmic web was just beginning to take shape. And they, if they still exist, if they have not been torn apart by mergers or consumed by black holes, are seeing us as we were 13 billion years ago, before the sun existed, before the Milky Way had its current form. We are all ghosts to each other, separated by time as much as by space, connected by light that carries information across the void. Information that is always out of date, always historical, always a record of what was rather than what is. The Great Attractor pulls us, but the Great Attractor we see is a ghost, an echo, a memory of something that existed 250 million years ago. And we are falling toward it. And we will continue to fall toward it, even though we will never reach it, even though the universe will tear us apart before we can arrive. This is what it means to live in an expanding universe shaped by invisible forces. This is what it means to discover that you are part of flows and structures that dwarf human comprehension. This is what it means to realize that the ground beneath your feet is not still, that you are hurtling through space at speeds that make a bullet seem motionless, that you have been falling your entire life without knowing it. And yet, there is beauty in this. There is wonder. Because we figured it out. We measured the invisible. We mapped the flows. We discovered Laniakea. We found the Great Attractor. We did this not with our eyes, which are blind to most of the universe, but with our minds, with mathematics and physics and the scientific method. We extended our senses beyond their natural limits. We built instruments that could see what we could not see. We developed theories that could explain what we observed. We created simulations that could predict what we would find. And we were right. The universe is comprehensible. That is perhaps the most astonishing thing of all. It follows rules. It has patterns. It can be understood. Not easily, not completely, but enough. Enough to know that we are falling toward the Great Attractor. Enough to map Laniakea. Enough to measure dark matter and dark energy. Enough to trace our cosmic address from Earth to the solar system, to the Milky Way, to the local group, to Laniakea, to the observable universe. Enough to know where we are, even if we do not yet know what we are made of, or where we are ultimately going. There is a photograph that changed everything. Not a photograph in the traditional sense, but a map, a visualization created from decades of painstaking observation. It shows the cosmic web in 3 dimensions, filaments of galaxies stretching across hundreds of millions of light-years, clusters glowing at the intersections, vast voids of emptiness between them. And there, highlighted in color, is Laniakea, our home supercluster. 520 million light-years across, 100,000 galaxies. And at its heart, the gravitational basin we call the Great Attractor. But here is what makes this image truly revolutionary. It does not show where galaxies are, it shows where they are going. The colors represent flow, motion, velocity fields mapped across cosmic scales. Every galaxy is an arrow pointing toward its gravitational destiny. And when you look at this map, you see something that no human had ever seen before. You see the shape of gravity itself, the invisible architecture that determines the fate of everything. This map was published in 2014 by Brent Tully and his team. It took 9 years to create, 8,000 galaxies measured, distances calculated using multiple independent methods, peculiar velocities extracted from redshift data, gravitational flows traced through 3-dimensional space. The result was not just a map of where things are, but a map of how things move, a dynamic portrait of the universe in motion. And it revealed something profound. The boundaries of Laniakea are not defined by where galaxies are located. They are defined by where water flows over a watershed divide. Imagine you are standing on a mountain ridge. Rain falls on one side and flows down toward the Pacific Ocean. Rain falls on the other side and flows down toward the Atlantic. The ridge is the boundary, the watershed divide. Laniakea has boundaries like this. Galaxies on one side of the boundary flow toward the Great Attractor. Galaxies on the other side flow toward different attractors, different gravitational basins. The Shapley supercluster, the Perseus-Pisces supercluster, the Coma supercluster. Each is a separate basin in the cosmic landscape, each with its own flows, its own destiny. This is a fundamentally new way of defining cosmic structure. Previous definitions of superclusters were based on density, on where galaxies clustered together. But Tully's definition is based on dynamics, on motion, on gravitational flow. It is the difference between a photograph and a video, between a static snapshot and a living, moving system. And it reveals something that static maps cannot show. The universe is not a collection of objects. It is a system of flows. Think about what this means. Every galaxy in Laniakea, including ours, is part of a single coherent flow pattern. We are not randomly scattered. We are organized by gravity into streams and rivers and currents, all converging toward a common center. The Milky Way is not just near Andromeda. We are both part of the same flow, falling together toward the Virgo cluster, which is itself falling toward the Great Attractor. We are connected not by proximity, but by motion, by shared destiny, by the fact that we are all following the same gravitational currents carved into space-time billions of years ago. But here is where the story becomes even stranger. The Great Attractor is not the end of the flow. It is a waypoint. Because Laniakea itself is moving. The entire supercluster, all 100,000 galaxies, all the dark matter scaffolding, all the flows converging toward the Great Attractor, is being pulled toward something even larger. The Shapley supercluster, 650 million light-years away, contains a concentration of mass so enormous that it dominates the motion of everything within a billion light-years. It is pulling Laniakea. It is pulling the Perseus-Pisces supercluster. It is pulling multiple other superclusters toward it. And we do not yet know what, if anything, is pulling Shapley. Let me give you a sense of the scales involved. The Great Attractor has the mass of tens of thousands of galaxies. Laniakea contains 100,000 galaxies. The Shapley supercluster contains more than 8,000 galaxies in its core alone, with a total mass that may exceed 10,000 times that of the Milky Way. It is one of the most massive structures in the observable universe, and it is pulling us toward it at a speed that, when combined with our motion toward the Great Attractor, means we are moving through space at over 600 kilometers per second relative to the cosmic microwave background, the afterglow of the Big Bang itself. 600 kilometers per second. That is over 2 million kilometers per hour. That is fast enough to travel from Earth to the Moon in 35 minutes. Fast enough to cross the diameter of the Sun in 2 hours. And we have been moving at this speed for billions of years, pulled by gravitational forces so vast they operate across distances that light takes hundreds of millions of years to cross. Now here is the question that keeps cosmologists awake at night. How do we know any of this is real? How do we know we are not making mistakes, seeing patterns that do not exist, inferring structures from noisy data? The answer lies in independent confirmation, in multiple lines of evidence that all point to the same conclusion. First, there is the cosmic microwave background. This is the oldest light in the universe, radiation left over from the Big Bang, emitted when the universe was only 380,000 years old. It fills all of space, a faint glow of microwave radiation coming from every direction. And it is almost perfectly uniform, the same temperature in every direction to within 1 part in 100,000. Almost uniform, but not quite. There are tiny fluctuations, hot spots and cold spots, variations in temperature of only a few millionths of a degree. These fluctuations are the seeds of all structure, the quantum fluctuations inflated to cosmic scales that became the galaxies and clusters and superclusters we see today. But there is something else in the cosmic microwave background. A dipole. One side of the sky is slightly hotter than the other. Not because the universe is actually hotter in that direction, but because we are moving through space. The Doppler effect shifts the radiation toward higher frequencies, higher temperatures, in the direction we are moving, and toward lower frequencies, lower temperatures, in the opposite direction. By measuring this dipole, astronomers can calculate our absolute motion through space relative to the cosmic microwave background. And the answer is 630 kilometers per second toward a point in the constellation Hydra. This is independent confirmation. We measured our motion by mapping galaxy flows. We measured our motion by observing the cosmic microwave background. Two completely different methods, and they agree. We are moving at 600 kilometers per second toward Hydra, toward the Shapley supercluster, pulled by gravity across cosmic distances. Second, there is gravitational lensing. When light from distant galaxies passes through the Shapley supercluster, it is bent by the gravity of all that mass. The images of background galaxies are distorted, stretched into arcs, sometimes split into multiple images. By studying these distortions, astronomers can map the distribution of mass in Shapley, including the dark matter. And what they find confirms the flow maps. Shapley is extraordinarily massive, massive enough to pull superclusters toward it across hundreds of millions of light years. Third, there are simulations. Cosmologists have created computer models of the universe, starting from the initial conditions measured in the cosmic microwave background, and letting gravity do its work over billions of years. These simulations include dark matter, dark energy, the expansion of space, all the physics we understand. And they produce a universe that looks remarkably like the one we observe. Filaments of galaxies, clusters at intersections, superclusters flowing toward massive attractors. The simulations predict structures like Laniakea and Shapley. They predict flows like the ones we measure. They confirm that what we are seeing is not an artifact of our observations, but a real feature of cosmic structure. So we know it is real. We are falling toward the Great Attractor. The Great Attractor is falling toward Shapley. And this raises a profound question. What does it mean for the future? Where are we going? What will happen when we get there? The answer is both simple and deeply unsettling. We will never get there. Not to the Great Attractor, not to Shapley, not to any destination beyond our local group of galaxies. Because the universe is expanding, and the expansion is accelerating, and dark energy is tearing the cosmic web apart faster than gravity can pull it together. Here is how it works. Right now, gravity dominates on small scales. The local group, containing the Milky Way and Andromeda and about 50 smaller galaxies, is gravitationally bound. We are close enough and massive enough that our mutual gravitational attraction overcomes the expansion of space. In about 4 billion years, the Milky Way and Andromeda will collide and merge, forming a single giant elliptical galaxy. This will happen. The expansion of the universe cannot prevent it because we are already too close, already falling toward each other too fast. But Laniakea is not gravitationally bound. The galaxies at the edges of the supercluster are far enough away that the expansion of space is pulling them away faster than gravity can pull them back. The flows we see today, the motion toward the Great Attractor, are the result of initial conditions set billions of years ago when the universe was denser and gravity was stronger. But those flows are slowing down. The expansion is winning. In the future, the galaxies at the edges of Laniakea will be pushed beyond the cosmic horizon, receding so fast that their light will never reach us again. Laniakea will shrink. The Great Attractor will become less great. Eventually, only the local group will remain, isolated in an expanding void. This is the ultimate fate of structure in an accelerating universe. Dark energy will tear apart everything that is not gravitationally bound. Superclusters will dissolve. Clusters will dissolve. Only the tightest groups of galaxies will survive, and even they will be alone, unable to see or reach any other groups. The cosmic web will be erased. The flows will stop. The universe will become a collection of isolated island universes, each one receding from all the others, each one eventually unable to see anything beyond its own local group. And it gets worse. Much worse. Because dark energy does not stop. In the far future, trillions of years from now, even gravitationally bound structures will be torn apart. First, galaxy clusters will dissolve. Then galaxies themselves will be ripped apart, stars flung into the void. Then solar systems will be destroyed, planets torn from their orbits. Then stars themselves will be shredded. Then planets. Then molecules. Then atoms. Then atomic nuclei. In the final moments, even the fabric of space-time itself will be torn apart in an event cosmologists call the Big Rip. The universe will end not in fire or ice, but in disintegration, everything pulled apart by the accelerating expansion of space. But that is trillions of years in the future. Right now, we live in the age of structure. We live in a time when galaxies cluster, when superclusters flow, when the cosmic web is visible. We live in a brief cosmic moment when the universe is old enough to have formed complex structures, but young enough that those structures have not yet been torn apart. We live in the era when discovery is possible, when we can look out and see the flows, map the attractors, trace our place in the cosmic web. And we have done exactly that. We have discovered that we live in Laniakea. We have found the Great Attractor. We have measured our motion through space. We have mapped the invisible. And in doing so, we have answered one of the oldest questions humans have ever asked. Where are we? What is our place in the universe? Our address is now complete. Earth, third planet from the Sun. Solar system, orbiting in the Orion arm of the Milky Way. Milky Way, a spiral galaxy containing 400 billion stars. Local group, a collection of about 50 galaxies dominated by the Milky Way and Andromeda. Virgo supercluster. No, wait, that is outdated. We do not live in the Virgo supercluster. We live in Laniakea, a supercluster 520 million light-years across, containing 100,000 galaxies, flowing toward the Great Attractor, which is itself being pulled toward the Shapley supercluster, which is located in the observable universe, which is a sphere 93 billion light-years across, containing 2 trillion galaxies, expanding and accelerating, shaped by dark matter and dark energy, governed by gravity and quantum mechanics, born in the Big Bang 13.8 billion years ago. That is where we are. That is our cosmic address. And every part of it was discovered by humans, by scientists using telescopes and mathematics and the scientific method, extending our senses beyond their natural limits, perceiving the invisible, measuring the immeasurable, comprehending the incomprehensible. But there is something else, something deeper, that this discovery reveals. It is not just about where we are, it is about what we are. We are not separate from the universe. We are part of it. The atoms in your body were forged in stars that lived and died billions of years ago. Those stars were part of galaxies that flowed through the cosmic web, pulled by the same forces that pull us now. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created in stellar furnaces, scattered into space by supernovae, incorporated into new stars and planets, and eventually into you. You are made of stardust. This is not a metaphor. It is literally true. Every atom in your body, except for hydrogen, was created in a star. And those atoms have been flowing through the universe for billions of years, following gravitational currents, falling toward attractors, part of the cosmic web. You are not just in the universe, you are of the universe. You are a temporary configuration of matter that has been falling through space since before Earth existed, that will continue to exist in some form long after you are gone, that is connected to everything else through the flows and forces that shape cosmic structure. This is what the Great Attractor teaches us. Not just that we are moving, but that we are part of something larger. Not just that the universe has structure, but that we are woven into that structure. Not just that gravity shapes galaxies, but that it shapes us. That we are products of the same forces that create superclusters and cosmic flows. And there is something profound in that realization. For most of human history, we believed we were separate from the cosmos, that Earth was the center, that we were special, that the universe revolved around us. Every discovery since then has been a step away from that belief. Earth orbits the sun orbits the galaxy. The galaxy is one of billions. We are not the center. We are not special. We are not separate. But we are not insignificant either. Because we are the part of the universe that can understand itself. We are matter that has become conscious, that can look out and see the cosmic web, that can measure the flows, that can discover the Great Attractor. We are the universe observing itself, understanding itself, marveling at its own complexity and beauty. Think about that. The atoms in your brain were forged in stars. Those atoms have arranged themselves into a structure complex enough to contemplate the universe that created them. You are a way for the cosmos to know itself. This is not mysticism, this is physics. You are a pattern of matter and energy, organized by the laws of nature, capable of perceiving and understanding those same laws. You are both observer and observed, both subject and object, both part of the universe and apart from it, able to step back and see the whole. And what we see is astonishing. We see a universe of unimaginable scale and complexity. We see galaxies flowing through space like rivers. We see dark matter scaffolding, holding everything together. We see dark energy tearing everything apart. We see the cosmic web, the largest structure in existence, shaped by gravity over billions of years. We see our place in it, our motion through it, our connection to it. We see that we are falling toward the Great Attractor at 2 million kilometers per hour. We see that we have been falling for billions of years. We see that we will continue to fall, even though we will never arrive, even though the universe will tear us apart before we can reach our destination. We see that we are part of flows and structures that dwarf human comprehension, that operate on scales of space and time that make our lives seem like brief flickers in an eternal cosmic dance. And yet, we see. We understand. We know. We have mapped the invisible. We have measured the immeasurable. We have discovered our place in the cosmos. And that is perhaps the most remarkable thing of all. Not that the universe is vast and complex and beautiful, but that we, tiny creatures on a small planet orbiting an ordinary star in an unremarkable galaxy, have figured it out. We have looked through the zone of avoidance and seen the great attractor. We have mapped Laniakea. We have traced the flows. We have measured dark matter and dark energy. We have calculated our motion through space. We have determined our cosmic address. We have done all of this in the last 50 years, a blink of an eye in cosmic time, using instruments and mathematics and the scientific method. This is the power of human curiosity. This is what we can achieve when we ask questions and refuse to accept easy answers. This is what happens when we build on the work of previous generations, when we share knowledge, when we collaborate across borders and cultures and disciplines. This is what science can do. It can reveal the invisible. It can measure the immeasurable. It can show us our place in the universe. But it can also show us how much we do not know. Because for every answer, there are new questions. We know we are falling toward the great attractor, but we do not know what dark matter is. We know the universe is accelerating, but we do not know what dark energy is. We know we live in Laniakea, but we do not know what lies beyond the limits of our observations. We know the cosmic web exists, but we do not know if there are even larger structures, even greater attractors, beyond what we can currently see. And that is as it should be. Science is not about having all the answers. It is about asking better questions. It is about pushing the boundaries of knowledge, about exploring the unknown, about discovering what we did not know. Every answer opens new doors. Every discovery reveals new mysteries. And that is what makes it exciting. That is what makes it worthwhile. We are falling toward the great attractor. We have been falling for billions of years. We will continue to fall for billions more. And we will never arrive. But we know we are falling. We have measured it. We have mapped it. We have understood it. And that knowledge, that understanding, that ability to perceive the invisible and comprehend the incomprehensible is what makes us human. It is what makes us remarkable. It is what makes us, in our own small way, as extraordinary as the universe we inhabit. There is a moment in every great discovery when the instruments become inadequate, when the questions outgrow the tools we have to answer them. We have reached that moment with the great attractor. We know it is there. We know it is pulling us. We know it sits at the heart of Laniakea, hidden behind the zone of avoidance, surrounded by structures so massive they defy easy comprehension. But knowing something exists and understanding what it truly is are two different things entirely. Let me tell you about the problem we face. The zone of avoidance is not a small inconvenience. It is a fundamental barrier that blocks roughly 20% of the observable universe from our view. Imagine trying to understand a painting when a fifth of it is covered by an opaque curtain you cannot remove. That curtain is the disk of our own galaxy, 10,000 light-years thick, filled with dust and gas and hundreds of billions of stars, all of it absorbing and scattering the light from anything behind it. Visible light cannot penetrate. Even infrared light, which can see through some of the dust, is blocked by the densest regions. This is why the great attractor remained hidden for so long. This is why, even now, with all our technology, we cannot see it clearly. We are like astronomers trying to observe the universe from inside a fog bank, knowing that something enormous lies beyond the fog, feeling its gravitational pull, but unable to see its true form. But science does not accept barriers. When one method fails, we invent another. When visible light is blocked, we use infrared. When infrared is blocked, we use radio waves. When radio waves are insufficient, we use X-rays. And when all electromagnetic radiation fails, we use something that nothing can block: gravity itself. In the 1990s, astronomers began using a new generation of radio telescopes to map the zone of avoidance. Radio waves have longer wavelengths than visible light or infrared, which means they can penetrate dust more effectively. The Parkes Radio Telescope in Australia, with its 64-meter dish, conducted systematic surveys of the southern sky, the region where the Great Attractor lies. Over years of observation, astronomers detected the radio emissions from thousands of galaxies hidden behind the Milky Way's disk. They measured redshifts. They calculated distances. They began to fill in the blank spaces on the cosmic map. What they found was both illuminating and frustrating. Yes, there were massive galaxy clusters in the zone of avoidance. The Norma cluster, containing dozens of large galaxies. The Centaurus cluster. The Pavo-Indus supercluster. Structures that had been completely invisible to optical telescopes suddenly appeared in radio surveys. But even when they added up all this newly discovered mass, it was not enough. The gravitational pull we measured, the force accelerating our galaxy and thousands of others toward this region, required more mass than they could account for. Either there was still more hidden structure they had not detected, or the Great Attractor was not a single object at all, but a confluence of multiple massive structures whose combined gravity created the pull we observed. This is where the story becomes less about a single destination and more about the nature of cosmic structure itself. Because what we call the Great Attractor may not be a thing. It may be a place, a region, a gravitational basin where multiple flows converge. Think of it like a whirlpool in a river. The whirlpool is not an object. It is a pattern, a configuration of flowing water created by the shape of the riverbed and the currents passing through it. The Great Attractor may be the cosmic equivalent, a gravitational whirlpool where the flows of Laniakea converge, created not by a single massive object, but by the combined gravity of multiple clusters and the dark matter scaffolding connecting them. This realization changes everything. It means we are not falling toward a destination. We are falling along a path, following the contours of space-time, carved by the distribution of mass across hundreds of millions of light years. The Great Attractor is not pulling us the way the sun pulls Earth. It is more like a valley we are rolling into, drawn by the slope of the gravitational landscape. But here is what makes this truly fascinating. That landscape is not static. It is dynamic, evolving, shaped by forces that operate on timescales of billions of years. The flows we see today are snapshots of a process that has been unfolding since the first galaxies formed. And that process is not random. It is deterministic, governed by the laws of physics, predictable in principle, even if we lack the computational power to calculate every detail. Scientists have created simulations of this process, and they are among the most ambitious computational projects ever attempted. The Millennium Simulation, run in 2005, tracked the evolution of over 10 billion particles, representing dark matter, over the entire history of the universe. It required 28 days of continuous computation on a supercomputer with more than 500 processors. The result was a virtual universe, a three-dimensional model showing how dark matter clumped together under gravity, forming filaments and clusters and voids, creating the cosmic web. When astronomers compared this simulation to observations of the real universe, the match was stunning. The simulated universe had structures that looked like Laniakea. It had flows that converged toward massive attractors. It had a zone of avoidance, where the view was blocked by the simulated Milky Way. The simulation predicted what we would see if we could map the real universe in perfect detail. And what we have mapped so far matches the predictions. This is not proof that we understand everything, but it is powerful evidence that we understand the fundamental processes. Gravity works the way we think it works. Dark matter behaves the way our theories predict. The cosmic web is not an illusion or an artifact of our observations. It is a real structure, created by real physical processes, operating according to laws we can write down in equations. But simulations have limits. They can model dark matter, but they cannot tell us what dark matter is. They can show us how structures form, but they cannot explain why the universe has the initial conditions it does. They can predict the large-scale structure of the cosmos, but they cannot account for every detail, every individual galaxy, every peculiar velocity. The universe is more complex than any simulation we can run, more detailed than any model we can build. And this brings us to a deeper question, one that goes beyond the Great Attractor, beyond Laniakea, beyond even the cosmic web itself. Why does the universe have structure at all? Why is matter not distributed uniformly through space? Why do galaxies cluster? Why do superclusters flow? Why is there something rather than nothing? And why is that something organized in this particular way? The answer, as far as we understand it, goes back to the first moments after the Big Bang. In the earliest fraction of a second, the universe underwent a period of exponential expansion called inflation. Space itself expanded faster than the speed of light, stretching quantum fluctuations to cosmic scales. These fluctuations were tiny, random variations in the density of matter and energy, differences of only 1 part in 100,000. But they were enough. When inflation ended and the universe began to expand more slowly, these density variations became the seeds of structure. Regions that were slightly denser attracted more matter. Regions that were slightly less dense became voids. Over billions of years, gravity amplified these tiny differences into the galaxies and clusters and superclusters we see today. This means the Great Attractor, the structure pulling us through space at 2 million kilometers per hour, is the descendant of a quantum fluctuation that occurred 13.8 billion years ago, in the first trillionth of a trillionth of a trillionth of a second after the Big Bang. A random fluctuation, amplified by inflation, shaped by gravity over cosmic time, became the gravitational basin at the heart of Laniakea. We are falling toward the echo of a quantum event that happened before atoms existed, before stars formed, before anything we would recognize as structure emerged from the primordial chaos. Think about the chain of causation. A quantum fluctuation in the inflaton field. Inflation stretches it to cosmic scales. The fluctuation becomes a region of slightly higher density. Gravity pulls more matter into that region. The matter forms the first stars. The stars form the first galaxies. The galaxies cluster. The clusters merge. Over billions of years, the structure grows, fed by the continuous infall of matter following the gravitational currents. And now, 13.8 billion years later, we are part of that infall, following a path that was set in motion before the universe was 1 second old. This is determinism on a cosmic scale. The future was written in the past. Not in detail, not every individual event, but the large-scale structure, the flows, the attractors, all of it was determined by the initial conditions. If we could know the exact distribution of matter and energy in the early universe, if we could measure every quantum fluctuation with perfect precision, we could, in principle, predict where every galaxy would be today, how fast it would be moving, where it would be going. The universe is not random. It is lawful. It follows rules. And those rules connect the smallest scales to the largest, quantum mechanics to cosmology, the first moment to the present day. But here is where I need to be honest with you. Here is where the scientific narrative becomes more uncertain, more speculative, more dependent on theories we have not yet confirmed. Because while we can trace the history of structure formation back to the Big Bang, we cannot explain the Big Bang itself. We do not know why the universe began. We do not know why it has the laws of physics it does. We do not know why the initial conditions were what they were. We can describe what happened, but we cannot explain why it happened. And there is something else, something that challenges the entire framework I have been describing. The measurements do not quite add up. When we measure the motion of galaxies in our local region, when we trace the flows toward the Great Attractor and beyond toward Shapley, we find velocities that are slightly higher than our models predict. Not by much, but enough to be noticeable. Enough to suggest that either our models are incomplete, or there is something else out there, some additional mass or structure beyond what we have detected, pulling on us in ways we have not accounted for. Some astronomers have proposed the existence of an even larger structure, something they call the Shapley concentration, or the Shapley Attractor, a region of space containing multiple superclusters with a total mass that might exceed anything else in the observable universe. Others have suggested that our measurements are affected by the expansion of space in ways we have not fully understood, that the relationship between distance and velocity is more complex than we thought. Still others have proposed modifications to our theory of gravity, suggesting that on the largest scales, gravity might behave differently than Einstein's equations predict. I am telling you this because it is important to understand the limits of our knowledge. We have discovered the Great Attractor. We have mapped Laniakea. We have traced the flows. But we have not solved all the mysteries. We have not answered all the questions. Science is not a collection of facts. It is a process, an ongoing investigation, a conversation between theory and observation that never ends. Every answer raises new questions. Every discovery reveals new puzzles. And there is something beautiful in that uncertainty, something honest. Because the alternative would be to pretend we know more than we do, to present a neat, complete story with no loose ends, no unanswered questions, no mysteries remaining. But that would be a lie. The universe is more complex than we understand. It surprises us. It challenges our theories. It forces us to revise our models, to build better instruments, to ask deeper questions. This is what separates science from pseudoscience. Science admits what it does not know. It quantifies uncertainty. It tests predictions. It changes its mind when the evidence demands it. Pseudoscience offers certainty, complete explanations, answers to every question. It sounds more satisfying, but it is not true. The universe does not owe us easy answers. It does not care if we understand it. It simply is, following its own laws, indifferent to our desire for comprehension. And yet, we comprehend. Not completely, not perfectly, but enough. Enough to know we are falling toward the Great Attractor. Enough to map Laniakea. Enough to trace our cosmic address. Enough to understand that we are part of something larger, something ancient, something that connects us to the first moments after the Big Bang and the ultimate fate of the universe billions of years in the future. Let me bring this back to something concrete, something you can visualize. Right now, at this moment, you are moving through space at 630 kilometers per second. That is your total velocity relative to the cosmic microwave background, the closest thing we have to an absolute reference frame. Of that 630 kilometers per second, about 370 comes from the motion of the local group toward the Virgo cluster. Another 200 comes from the motion of the Virgo cluster toward the Great Attractor. And the remaining 60 comes from the motion of Laniakea toward the Shapley supercluster. These are not separate motions. They are nested, layered, each one adding to the others. You are moving because Earth orbits the Sun. The Sun orbits the Milky Way. The Milky Way falls toward Andromeda. The local group falls toward Virgo. Virgo falls toward the Great Attractor. Laniakea falls toward Shapley. Each motion is caused by gravity, by the pull of mass across space, by the shape of the cosmic landscape carved over billions of years. And here is what makes this visceral, what makes it real. You have been moving at this speed your entire life. Every breath you have taken, every step you have walked, every word you have spoken, you have done while hurtling through space at 630 kilometers per second. You have traveled trillions of kilometers since you were born, following gravitational currents you never felt, falling toward destinations you will never reach, part of flows that connect you to the largest structures in the universe. You cannot feel this motion because everything around you is moving with you. The ground beneath your feet, the air you breathe, the planet, the solar system, the galaxy, all of it is falling together. There is no wind in your face, no sense of acceleration, no indication that you are moving at all. And yet, you are. You have always been. You will always be, until the expansion of the universe tears apart even the structures that bind us together. This is the reality we inhabit. This is the universe we have discovered. Not a static cosmos with Earth at the center, but a dynamic, evolving, expanding universe where everything is in motion, where galaxies flow like rivers, where superclusters rise and fall like waves on a cosmic ocean, where we are passengers on a journey that began before we existed and will continue long after we are gone. And we figured this out. We, humans, creatures who evolved on a small planet to hunt and gather and survive, have extended our minds across the cosmos. We have built instruments that can see what our eyes cannot. We have developed mathematics that can describe what our intuition cannot grasp. We have created theories that can predict what we have not yet observed. We have mapped the invisible. We have measured the immeasurable. We have discovered our place in the universe. But discovery is not the end. It is the beginning. Because now that we know we are falling toward the Great Attractor, now that we have mapped Laniakea, now that we understand the cosmic web, we can ask deeper questions. What is dark matter? What is dark energy? Why does the universe have the structure it does? What lies beyond the limits of our observations? Are there even larger structures, even greater attractors, beyond what we can currently see? And ultimately, what does it all mean? What is our place, not just in space, but in the story of the cosmos? These are not just scientific questions. They are philosophical questions. They are questions about meaning and purpose and significance. They are questions that science alone cannot answer, but that science makes possible to ask. Because only by understanding where we are, how we got here, where we are going, can we begin to grapple with the deeper question of why. Why does the universe exist? Why does it have the laws it does? Why are we here to observe it? These are questions that have haunted humanity for millennia. Questions that every culture has tried to answer in its own way. And now, for the first time in history, we have the tools to approach these questions not with mythology or speculation, but with observation and measurement and reason. We may never have complete answers. The universe may be fundamentally mysterious, its deepest truths forever beyond our reach. But we can push the boundaries. We can explore the unknown. We can discover what we did not know we did not know. And in doing so, we can find meaning not in easy answers, but in the search itself, in the act of questioning, in the endless pursuit of understanding. This is what the Great Attractor teaches us. Not just that we are moving, but that we are part of a story larger than ourselves. Not just that the universe has structure, but that we can comprehend that structure. Not just that we are falling through space, but that we can measure our fall, map our trajectory, understand our place in the cosmic flow. We are falling toward the Great Attractor at 2 million kilometers per hour. We have been falling for billions of years. We will continue to fall for billions more. And we will never arrive. But we know we are falling. And that knowledge, that understanding, that ability to perceive the invisible and comprehend the incomprehensible is what makes us human. It is what makes us remarkable. It is what makes us, in our own small way, as extraordinary as the universe we inhabit. The journey continues. The questions deepen. The mysteries remain. And that is exactly as it should be. There is a question that sits at the boundary between physics and philosophy. A question that every discovery about the universe makes more urgent and more profound. If we are falling through space at 2 million kilometers per hour, if we have been falling for billions of years, if we will continue to fall forever toward destinations we will never reach, then what does it mean to be still? What does it mean to be home? What does it mean to say that you are here, in this place, at this moment, when here and now are coordinates in a reference frame that is itself in motion, falling through a universe that is expanding, accelerating, tearing itself apart? The ancient Greeks believed in the unmoved mover, a fixed point around which everything else revolved. Medieval astronomers placed Earth at the center of nested crystalline spheres. Even Einstein, when he first applied his equations to cosmology, added a term to keep the universe static, because he could not accept that everything was in motion. We crave stillness. We crave a foundation. We crave something absolute, something fixed, something we can point to and say, this is the center, this is home, this is where I am. But the universe offers no such comfort. There is no center. There is no fixed point. There is no absolute reference frame. There is only motion, endless motion, flows within flows, structures falling toward other structures, all of it expanding, all of it temporary, all of it destined to dissolve as dark energy tears the cosmic web apart. You are not standing still. You have never been standing still. You will never be standing still. You are falling, and you have been falling since before you were born, and you will continue to fall until long after you are gone. And yet, here is the paradox. You feel still. Right now, as you absorb these words, you feel motionless. The ground beneath you feels solid. The air around you feels calm. You have no sensation of hurtling through space at 630 kilometers per second. You cannot feel the rotation of Earth, or its orbit around the Sun, or the Sun's orbit around the galaxy, or the galaxy's fall toward Andromeda, or the local group's fall toward Virgo, or Virgo's fall toward the Great Attractor, or Laniakea's fall toward Shapley. You feel none of it. And in a very real sense, you are still. Because stillness is not absolute. It is relative. You are still relative to everything around you. You are still relative to the ground, the air, the planet, the solar system, the galaxy. You are moving relative to the cosmic microwave background, but you are still relative to your local environment. And that is the only stillness that matters. This is what Einstein taught us with relativity. There is no privileged reference frame. Motion is always relative to something else. You can say you are moving at 630 kilometers per second relative to the cosmic microwave background. You can also say you are motionless relative to Earth. Both statements are equally true. Both are valid descriptions of reality. The universe does not care which reference frame you choose. The laws of physics work the same in all of them. But there is something deeper here, something that goes beyond physics into the realm of human experience. Because while motion may be relative, meaning is not. The fact that you are falling through space at incomprehensible speeds does not diminish the significance of your life. The fact that Earth is a tiny speck in an unimaginably vast universe does not make your existence less important. The fact that we will never reach the Great Attractor, that Laniakea will dissolve, that the cosmic web will be torn apart, that everything we can see will eventually disappear beyond the cosmic horizon, none of this makes the present moment less real, less valuable, less worthy of attention and care. This is the mistake that people make when they first confront the scale of the universe. They feel diminished. They feel insignificant. They look at the numbers, the distances, the timescales, and they think, what does my life matter in the face of all this? What difference does anything I do make when the universe is so vast and I am so small? But this is backwards. The universe is not vast to make you feel small. The universe is vast because that is what it takes to make you possible. Every atom in your body was forged in a star. Those stars required billions of years to form, to live, to die, to scatter their enriched material into space. That material required gravity to pull it together into new stars, new planets, new worlds. That gravity required the cosmic web, the flows, the attractors, the structures that span hundreds of millions of light years. All of it, the entire incomprehensible vastness of the universe, was necessary to create the conditions for your existence. You are not small compared to the universe. You are the universe, concentrated into a form complex enough to contemplate itself. You are what happens when hydrogen, given 13.8 billion years, evolves into consciousness. You are the mechanism by which the cosmos comes to know itself. And that is not insignificant. That is extraordinary. Think about what had to happen for you to exist. The Big Bang had to occur with exactly the right properties. If the expansion rate had been slightly different, if the density of matter had been slightly higher or lower, if the strength of gravity had been slightly stronger or weaker, stars would not have formed. Galaxies would not have formed. Planets would not have formed. You would not exist. The universe had to be precisely tuned, not for your benefit, but in such a way that your existence became possible. Then, quantum fluctuations in the inflaton field had to be amplified by inflation to create the seeds of structure. Those seeds had to grow under gravity for billions of years, forming the first stars, the first galaxies, the cosmic web. One of those galaxies had to be the Milky Way. One of its spiral arms had to contain a cloud of gas and dust that collapsed to form the Sun. That collapse had to leave behind a disk of material that coalesced into planets. One of those planets had to be at exactly the right distance from the Sun, with exactly the right mass, with exactly the right atmosphere to allow liquid water to exist on its surface. Then, chemistry had to become biology. Self-replicating molecules had to emerge from the primordial soup. Those molecules had to evolve over billions of years, through countless generations, through mass extinctions and environmental catastrophes, through the slow, blind process of natural selection, until eventually, 4 billion years later, they became you. A creature capable of looking up at the night sky and asking, "Where am I? What is this place? What does it mean?" Every step of this process was necessary. Every step was improbable. Every step depended on the steps before it. And yet, it happened. You are the proof. You are the result of 13.8 billion years of cosmic evolution, of structure formation and stellar nucleosynthesis and planetary accretion and biological evolution. You are the universe's way of understanding itself. And that is not small. That is not insignificant. That is miraculous. But here is what we do not know. Here is where the scientific narrative gives way to mystery, to questions we cannot yet answer, to possibilities we can barely imagine. We do not know if we are alone. We do not know if consciousness is common in the universe or rare. We do not know if there are other beings, on other planets, orbiting other stars, in other galaxies, also falling toward their own great attractors, also looking up at their own night skies, also asking the same questions we ask. The universe contains 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Many of those stars have planets. Some of those planets are in the habitable zone, where liquid water can exist. The numbers suggest that life should be common, that consciousness should be widespread, that we should not be alone. And yet, we have found no evidence of other intelligent life. No radio signals, no megastructures, no signs of civilizations that have spread across their galaxies. The universe appears empty, silent, devoid of anyone else asking these questions. This is the Fermi paradox. If life is common, where is everyone? Why do we see no evidence of other civilizations? There are many possible answers. Perhaps life is common, but intelligence is rare. Perhaps intelligence is common, but technological civilization is rare. Perhaps technological civilizations are common, but they destroy themselves before they can spread across the stars. Perhaps they are out there, but we are not looking in the right way, or they are not communicating in ways we can detect, or the distances are simply too vast for contact to be possible. Or perhaps we are alone. Perhaps the chain of events that led to our existence is so improbable, so dependent on unlikely coincidences, that it has happened only once in the observable universe. Perhaps we are the only consciousness, the only observers, the only beings capable of understanding the cosmos. Perhaps the universe created us not because we are common, but because we are unique. I do not know which answer is true, no one does. But I know this: whether we are alone or one of many, whether consciousness is rare or common, whether the universe is full of life or empty except for us, the fact remains that we are here. We exist. We are conscious. We can observe and understand and marvel at the cosmos. And that is enough. That is more than enough. That is everything. Because here is what the great attractor ultimately teaches us. It teaches us that we are part of something larger than ourselves. It teaches us that we are connected through gravity and motion and the flows of the cosmic web to structures that span hundreds of millions of light years. It teaches us that we are not separate from the universe, but woven into its fabric, made of its matter, shaped by its forces, following paths that were set in motion billions of years before we existed. But it also teaches us something else. It teaches us that understanding is possible, that the invisible can be measured, that the immeasurable can be comprehended, that we, tiny creatures on a small planet, can reach out with our minds and our instruments and touch the largest structures in existence, that we can map the flows, that we can discover the attractors, that we can trace our cosmic address from Earth to Laniakea to the observable universe, that we can know where we are, even if we do not yet know why we are. This is the gift of science. Not certainty, not complete answers, not an end to mystery, but the ability to ask better questions, to push the boundaries of knowledge, to explore the unknown. Science does not diminish wonder, it amplifies it. Every discovery reveals new depths, new complexities, new mysteries. The more we learn, the more we realize how much we do not know. And that is not a failure. That is the point. That is what makes the journey worthwhile. We are falling toward the great attractor at 2 million kilometers per hour. We have been falling for billions of years. We will continue to fall for billions more, and we will never arrive. The expansion of the universe will tear us apart before we can reach our destination. Laniakea will dissolve. The cosmic web will be erased. In the far future, only isolated island universes will remain, each one alone, unable to see or reach any others, falling through an expanding void toward nothing. But that is the far future. That is trillions of years away. Right now, we live in the age of structure. We live in a time when galaxies cluster, when superclusters flow, when the cosmic web is visible. We live in a brief cosmic moment when discovery is possible, when we can look out and see the flows, map the attractors, understand our place in the universe. We live in the era when consciousness has emerged, when matter has become aware of itself, when the universe can observe and understand its own structure. And we are doing exactly that. We are observing. We are understanding. We are mapping the invisible. We are measuring the immeasurable. We are discovering what we did not know we did not know. And in doing so, we are fulfilling a purpose that may be the only purpose that matters. We are the universe coming to know itself. We are the mechanism by which the cosmos becomes conscious of its own existence. We are the way that matter, given enough time and the right conditions, learns to contemplate the stars. Do you remember how this began? Do you remember the first words you read? Right now, as you sit perfectly still, you are hurtling through space at 2 million kilometers per hour. Not because Earth is spinning, not because we orbit the sun, not even because our solar system circles the Milky Way. Something else is pulling us, something massive, something we cannot see, and it has been dragging our entire galaxy toward it for billions of years. We have come full circle. We started with motion, with the revelation that we are falling through space at incomprehensible speeds. We trace that motion to its source, to the great attractor, to Laniakea, to the cosmic web. We explored the science, the observations, the measurements, the theories. We confronted the mysteries, the uncertainties, the limits of our knowledge. And now, at the end, we return to where we began, to you, to this moment, to the fact that you are falling, and you have always been falling, and you will always be falling. But now you know. Now you understand. Now you can look up at the night sky and see not just stars, but galaxies. Not just galaxies, but flows. Not just flows, but the cosmic web, the largest structure in existence, shaped by gravity over billions of years. You can see your place in it. You can trace your motion through it. You can understand that you are part of something larger, something ancient, something that connects the smallest scales to the largest, quantum fluctuations to superclusters, the first moment after the Big Bang to the present day. And perhaps that is enough. Perhaps that is all we can ask for. Not certainty, not complete understanding, not an end to mystery, but the knowledge that we are part of the universe, that we are connected to it, that we can observe and understand and marvel at it, that we can fall through space at 2 million kilometers per hour and still find meaning, still find purpose, still find beauty in the journey. We are falling toward the great attractor. We will never arrive, but we know we are falling. And that knowledge, that understanding, that ability to perceive the invisible and comprehend the incomprehensible is what makes us human. It is what makes us remarkable. It is what makes us, in our own small way, as extraordinary as the universe we inhabit. The cosmos is vast. We are small. But we are not insignificant. We are the part that knows. We are the part that understands. We are the part that asks why. And as long as we continue to ask, as long as we continue to explore, as long as we continue to push the boundaries of knowledge and reach out toward the unknown, we are fulfilling the only purpose that truly matters. We are the universe, awakening to itself. We are matter, becoming conscious. We are the great attractor, observing its own pull. We are falling through space, and we know we are falling, and that makes all the difference. Perhaps the questions are more important than the answers. Perhaps the journey is more meaningful than the destination. Perhaps the fact that we can ask these questions, that we can contemplate our place in the cosmos, that we can measure the invisible and map the immeasurable, is itself the answer we have been seeking all along. We are here. We are conscious. We are falling. And we are aware of our fall. That is not insignificant. That is everything.